Well, today you see here the roadmap should be a little bit relaxing compared to the other more formal lectures. Still, we will have one part where theory will enter, the theory that we get, we conquered, no, well, with which we have been becoming friends, in the sense that the source spectra that we deduced from the Haskell model, so one of the simplest extended source model that we treated, it will be revisited today from the point of view of magnitude, that is today's topic in some way.
Professor.
Yes. Hello. Good morning.
It's me. It's Tarek.
Yeah. No. I was saluting Maria Aurora. Tell me.
Okay. About the Haskell model, I just wanted to ask you, are we considering in a Haskell model that we are in the far field, we are very far from the source, or we are not that far, we are between near and far?
Okay. Now, that could be a good question. Let me try to prepare a sort of a good answer. Now, remember that when we studied the representation of the theorem, we discovered the term near source, far source. Near source means that the source cannot be considered as a point, okay?
Yeah.
So it's extended. When we treated the Green's function, we discovered near field, far field. So yes. Near source, far source, near field, far field, these are four conditions, 2 by 2. In the Haskell model, we are in the near source condition, so the source is not a point, but we are, for every sub-source, we are so far that we can exclude near field. So we are in the near source condition and far field condition. Remember that far field, we defined the far field considering the Green's function. And the Green's function can be defined, is defined for a point source. Okay? It's an impulse in space, in time, and direction. And we discovered near and far field. Okay?
Yeah.
So in the Haskell, we are in the far source, near source, the source is extended, and for every subsegment,
so for every subsegment, we are in a far field.
Yep.
That's it.
Now, if you want to take a little bit more complicated model than the Haskell, you can imagine to take your fault with your length, with your width, with the
please,
rupture.
Professor.
Pardon?
If you can just push the button of sharing slides and Blackboard in the desk.
It's already Blackboard plus slides.
No, because we're in the recording we have just the slides, not Blackboard plus slides.
I understand what you're asking, but the button here is Blackboard plus slides.
Okay, you push it now. You pushed it now.
It was already on. I'm pushing again, but.
Okay, it's okay.
If you want, I can change it.
No, because in the previous videos that they are in YouTube now, we can just see only the Blackboard or only the.
Tarek, I fully understand your question, but I cannot do more than this. It was always on.
Now it's okay. Now it's okay. Since you pushed the button.
Okay, Tarek, again, I have been pushing the button but it was already on. And also during the last lecture, it's on. So,
okay, so
I repushed it.
Okay.
So, okay, now let me go back again to this. So we have an extended fault. Let's imagine to divide it. But do you see the blackboard? Yes.
Yeah.
Okay. Now,
Yes.
Okay. So let's imagine that you have the rupture is starting from one point. The rupture is going to propagate in space and time with a given rupture velocity. Okay. Now, when the rupture is arriving at a given subsource, this subsource can be treated as a point source. So you can replace it with a double couple, okay? Now, for this double couple, if you properly divide the fault, this element here is mole, so it can be considered as a point source. Now, from this point source, you imagine to be in the far field, okay? So we are in the near source, but far field condition. That's the Haskell model. Okay?
Now I see.
Okay, so please do remember that the condition of near source, far source means one thing, and the condition of near field, far field means another thing. You can couple them. For example, you can stay in the near source and near field. So now, in the double couple, you have to include also the near and intermediate terms in that summation. So, again, the receiver is at a distance, let's put this, that is not large compared to L, but then you can imagine that for every subsource, it's large so that the near field term can be neglected and you keep just the terms that are decaying as 1 over distance. Okay?
Okay.
That's the Haskell model. And please do remember that thanks to the Haskell model, we got a simple source model.
Yeah,
Flat,
omega square model.
Yes, flat, and this depends on M0, 1 over omega squared. Now, about these two terms here, one is related to 2 over TR, and the other one is related to 2 over tau. This is the Haskell model and the source spectrum that we can deduce from it. We are going to use this today, okay? Okay, good. Now let's start. Today's topic is about the development of the idea of how to measure the size of an earthquake. That's a tough, it's a tough mission because it's pretty much impossible to squeeze this information in single numbers. The aim of magnitude is this, trying to describe the energy of an earthquake. Now, we discovered during the last lecture that instrumental seismology started. Do you see my screen shared?
Yes.
So with the full slide, right?
Yes.
Okay. Now, we discovered that instrumental seismology started, let's say, 1906, but real instrumental seismology started in 1920. Then the big development in the 1950s, 60s, 70s, and whatever. So please do remember that before we cannot rely on seismograms. So how to measure the earthquake size? Well, one of the first answers was to measure the effect of an earthquake on the human anthropic system. So on buildings, on bridges, on roads, on whatever. Of course, and that's intensity. But please, and we will spend a couple of slides about intensity, that is nowadays, again, an important data set. Why? Because it's the only data that we can collect from historical earthquakes. What does it mean? Historical, pre-instrumental. But there is one difference, well, there are many differences between intensity and magnitude. And the key issue is that intensity is not a single number. You have an earthquake, and you are going to measure or to describe or to collect the effects on the, for example, urban settlements and something like that. But you may have many numbers for one earthquake, while magnitude aspires to be one number. So that's the difference. And we will see how the evolution of the definition of magnitude will result in what we call MW, whose aim is to be a single number describing energy. But we will see also the tricky part, that is in practice, not in theory. And let me tell you since now that your homework for Monday will be a nice reading of a couple of pages, a paper published by Seth Stein and Emil Okel. The one that you can find on Moodle is about the 2004 26 December Sumatra earthquake, because the story telling of its magnitude was going from the, how to say, after 1 hour, a couple of hours of the event, it was issued as a magnitude 8 point something, then increasing, and after some days, seismological community realized that that number was too low, and that's why studying using other data, long period data, like the Earth free modes, Stein and Okel estimated the magnitude to be 9.2. That's a tricky part. It will be a very nice reading, and that's your homework. So the paper that you can find on Moodle. By the way, let's try to start with this topic today, intensity and magnitude. So this is what we want to describe. Okay, intensity has some cons on its side because it's supposed to be a dated method. It's not based on recordings, but that's also its pro side, because you can assess intensity for historical earthquakes. Many problems, yes, but it's still the only valuable tool trying to assess past historical earthquakes. While magnitudes, okay, they are supposed to rely on data, and we will see that. Now, what about intensity? Okay, the typical expression of intensity, and okay, intensity is a very important parameter. I'm squeezing here it in just a couple of slides here. It's not exactly the realm of theoretical seismology, but it's important if you're going to work in seismic hazard, for example. So that's why I'm putting here this couple of slides here. Now, that's an idea. Usually intensity is expressed as a set of integer numbers that are representing grades on a scale. There are many scales in the world. Yep, confusion is large under our skies because we have, the history is fascinating. It was starting in Italy, then in Switzerland, than in Eastern Europe, than in US, with many names, but the idea is to assign a degree, so an integer number, according to the effect on anthropized systems like buildings. The modern definition of magnitude, of intensity, sorry, is, for example, in the European, it's called EMS, European Microseismic Scale. Now it's also distinguishing between buildings and their vulnerability. Because you can imagine, for example, that if you are considering an earthquake in Japan with modern cities, with anti-seismic designs, and you consider the same earthquake, for example, in central Italy, where we have middle-age, medieval, urban, small towns, the effect will be totally different because vulnerability is different. We're going to say a few words in one of the final lectures during the next week. So you do understand the intensity is a tricky issue because in principle it should be based also on the concept of vulnerability. But to keep things simple here, we can decide to establish a set of degrees according to the effect that an earthquake is causing on buildings. Then you try to put these numbers, and of course, you need to have urban habitats somewhere. So if you stay in the desert, or if you stay in Antarctica, collect intensity values is pretty much impossible. So you may have a sort of, as a paradox, you may have intensity 0 with a large earthquake. But okay, if you have urban habitats, you can go there. Now there are surveys that are released by email. Otherwise, you go there, you investigate, you make some interviews, and you ask, okay, have you felt it? Did you felt it? Did you feel it? Okay, yes, no, how much? You look at the damages in the buildings and you put degrees. And then you try to make a sort of a contour lines, trying to put together the numbers with the degrees with an equal number. And usually, in the hypocentral zone, you should have the largest numbers. And these are called macroseismic maps. That's the idea of intensity. Let me add a few words about this. Well, it's not. Okay, let's see. Right? There are some issues, important and modern issues, using intensities, because, for example, if you consider a typical paradox in US seismic hazard, and if you compare, for example, the 1906 earthquake that we have seen, it has been recorded in Japan, one of the first recordings there. And if you draw the macroseismic lines in California, you see usually they are narrow. You have there the example of the San Francisco earthquake, or the Landers earthquake, 1992. And if you consider one of the past earthquakes, and it was not an instrumental earthquake like it's called the Missouri, it has many names. Nothing is sure about this earthquake, neither if it is 1 or 2, but if you give a look to this map here, you see that they are large. And why they are large? Because actually intensity as an intrinsic is revealing as an intrinsic expression also the geological conditions. So for example, and we will see this also during the next week, when I'm going to show to you some slides about what is called the Michoacan event of 1985, you could see that the largest intensity lines are in Mexico City, 400 kilometers far from the source. So it's tricky because site effects are entering into the macroseismic lines. Other geological conditions, and we will discuss one of these on Monday when we will try to consider the Q of the Earth and elasticity. So, for example, in Central, Eastern United States, the Q values, what does it mean? The attenuation factors compared to California, they are much lower, the attenuation. So Q is much higher. What does that mean? That seismic waves can propagate much more efficiently. And that's why these lines are much broad with the same numbers as you see here. So these are tiny squeezed, these are large. And looking at these maps, you immediately have a feeling that intensity, okay, is telling us something, but it's not, it's a very essential descriptor of the effects of an earthquake, but it's not an intrinsic measure of the energy of an earthquake. By the way, let me state it again, it's an invaluable tool because it's the only one that we can use to try to estimate earthquakes in the past, like earthquakes in the ancient Mediterranean area. There are many important there, or in China, or, okay, we studied many earthquakes also in northern Italy, in southern Italy, earthquakes that occurred in 16 something. We have no other way than using intensity, reading historical reports and say, okay, the bell tower of that city collapsed after this date, and it's a mess, it's not easy. Actually, this is a branch that is considered by people that is working in seismology, but especially in historical records. So historical seismology is a different branch, is a sort of a humanistic branch of seismology. I'm not part of that, but it's very important. So intensity, this is the idea. And to have a better idea and to show to you how complicated it could be, I was reporting this table here, some acronyms that could be useful if in the future you're going to consider them, just to show to you how many scales are available. And MM stands, for example, for modified Mercalli. And Mercalli was one of the fathers of intensity scales. He was working and studying in Italy at the end of the 19th century. And first he proposed a scale based on 10 degrees, so from 1 to 10. Then it has been modified by De Rossi. Then it was being modified by other people. And then in US, after Richter, they decided to create a new scale based on the Mercalli, that's why it's called modified Mercalli, based on 12 degrees. So if you, MM usually is used in the United States. Rossi Forelli is a scale that is a sort of the evolution of the original Mercalli one. MCS or actually MSK is one that is that has been developed especially in the eastern part of Europe and still used. MCS stands for Mercalli-Cancani-Sieberg, that is the father or the mother of a modern European scale. And just to make the story more complicated, Japanese adopt a totally different one that is called JMA by Japanese Meteorological Agency, that originally was based on 7 degrees, but actually they divided the 6th and the 7th grade into sub-degrees, so actually they are using 10 or 12 as well. So when you read a report about an historical earthquake, please be sure to read which is the macroseismic scale that is used. Every degree in this table here should have a description. I think I put one, oh, I was hiding it. Where is it? Okay, let me show to you just to have an idea. This is not today's topic, EMS. Let's see if I can find the links, PGR, what is it? Oh, God. Let's see if we can use this one. Let's see if I have a description. As you can see, there is a huge amount of literature about this. And for example, this is a typical description of vulnerability. Because in modern scales, you cannot say, okay, a building has totally collapsed, let's put 10. Well, no, you have to say if that building, for example, was a masonry building or reinforced concrete, because the quality of a building, so things can be divided into what are called vulnerability classes. And then according to the effect and to the vulnerability class, then the degree is assigned. Okay, you can see something like that here. So this is more a stuff, how to say, a stuff that is worked by geologists and civil engineers and people studying history. So that's how to put the grades for intensity in this case. Okay, but our today's topic is about something a little bit different, because it's an idea to overcome this definition and to go directly to the energy that can be released by an earthquake, and to express it as a sort of a single number, also if it is pretty much impossible, but to have an idea of the energy using a single number, so not many numbers as intensity degrees in an area. And the idea was to use the technological advance that we explored during the last lecture. We can call it seismometry. And here the history starts, because the starting of the magnitude concept, that is, if you want, today's topic, started, as I already told you, as I've already been telling to you, in 1935, thanks to Charles Richter. And this is a sort of a replot of his idea, sorry. He was able, at that time, to collect, let's say, a huge bunch of data compared to the previous years, of course, because he was in California. So it's an active zone for local earthquakes, for other American earthquakes that are coming from Mexico, from Guatemala, from Chile, with different energies, of course. And he had a seismic network using Wood Anderson. So he was aware that he was using a specific instrument, but he was collecting. Jacobo, are you there? Oh, Jacobo, welcome to today's. Okay, thank you. So you've reached off your microphone. And he was beginning to make some plots. Plots of what? Well, you see on the y-axis there is the logarithm of the amplitude. Of what? Well, let's imagine to take a seismogram and to plot the peaks of the seismogram. And he was noticing that according to the distance, the logarithm of the amplitude was, as we can get by intuition, was getting smaller on average. Why? Well, we have many candidates here, and the first one is geometrical spreading, because spherical waves and surface waves, they decay as 1 over distance or as 1 over the square root of distance. Of course, we can have bumps. Due to what? Well, we have candidates, radiation pattern, or, but this is another topic, local amplification due to impedance contrasts, so geology. But on average, they were decaying. And according to the earthquake, they were starting from a value and then decaying. So the idea was, yes?
Can I ask a question?
Yes.
I was wondering if the directivity has something to do with the magnitude here, because you said just source spectrum and geometrical spreading, and okay, it should be in geometrical spreading.
No, well, Tarek, let's try again. Let's try to put some order here. One thing is a propagation issue, and geometrical spreading is a propagation issue. Yeah. So on average, spherical and surface waves, they decay as in the far field as 1 over r or as 1 over square root of r. Do we agree on this?
Yes.
Good. And let's call it propagation. It's not a good label, but we can call it propagation effect. Then there is another propagation effect, but actually they are all together, but we can call it local amplification when you have sediments. Wait for the next week. Are we okay up to this point?
Yes.
Okay, good. Now let's imagine to consider the source. Let's imagine to be in the far field and in the far source. In the far source, we have no directivity, right?
Yes.
So the first factor that is affecting at large distances, different amplitudes, is radiation pattern. Do we agree on this?
Yes.
Good. Now let's imagine to be near to the source. And now we will have a feeling about rupture time and rise time. Do we agree on this?
Yes. Yes.
Good. Now look at these numbers here. They start from 100 kilometers until 600 kilometers. We are very far from the source. Okay?
Okay.
So at this stage here, we have in our background directivity, but it's not effective now. It will be effective, but not now, not for Richter.
Okay.
Not with these distances. It is there, but actually it's hidden in the first part of the plot. Okay?
Okay.
Have I answered?
Okay. Yeah. Okay.
Good. Now let's imagine to make these plots here. And so his idea, and I put an additional slide here for a better explanation, I hope, was, okay, can we equalize the amplitudes of the different earthquakes? Maybe they are tiny earthquakes, but very near, relatively near, or large ones, but very far. Can we put them all together at the same distance, and let's measure the difference from that distance? So the tricky idea was to use this equalization with the reference earthquake. If you do remember, during the last lecture, we discussed, I told you something about sound intensity level. We discussed also the dynamic range of instruments. And there was the trick of doing the logarithm of something over a reference value. Do you remember? Do you? Don't you? That's called dynamic range. During the last lecture, we discussed dynamic range of an instrument as 20 times the logarithm of the ratio of the maximum amplitude over the minimum one. I hope you do remember. It was one slide of the last lecture. Then I told you, okay, also the sound intensity level in acoustics usually is computed like that, using intensity, or if you prefer, amplitude, and then that becomes 20 logarithm of P over P0. Now, the key point is that, and also astronomers, to discuss luminosity of stars, since they have to handle large scales of variation, they use logarithm of something over a reference. Do you remember this?
Yes.
Okay. Now, Richter's idea was exactly the same. Very simple. He decided to use a reference amplitude. And if you want, the words are, okay, the amplitude that we would get from an earthquake at 100 kilometers from the receiver, from the seismometer, and that magnitude, if it is giving, if that earthquake, if it is giving 1 micrometer on a Wood-Anderson instrument, let's call it the reference amplitude. Okay. Now let's take all the other amplitudes compared to this one. And you do exactly like that. So it's a very simple idea to equalize all the other amplitudes compared to the reference one. Now you could say, why 1 micrometer at 100 kilometers? Well, because that was the amplitude that the Wood-Anderson was able to collect before entering into the noise. So that was the smallest amplitude that could be recorded with scientific accuracy. All the other ones can be compared to that one. And of course, with this definition, in principle, you can have negative magnitudes because all the amplitudes that are smaller than A0 will result in a negative value. But at that time, that was the smallest one that you can record with a given accuracy before being lost in the noise. But nowadays, with sensitivity on the instruments has increased, of course, now you can say for local earthquakes, for tiny local earthquakes, you have plenty of negative magnitudes. But at that time, okay, that was the, sorry, Jacobo, are you writing? Okay, thank you. Yes, we know. So based on this definition, all the other magnitudes at that time would be positive. Now let's try to have a sort of a better, I hope, look to this definition here. First, I decided to add here one of the original plots. This is coming from the book published by Richter and Gutenberg. And you see, it has been redrafted from the original notes. I'm sorry if the picture is not very high quality, but I took it. So you see, the idea here was to put some order in these messy points, but they were decaying on average, following what Richter observed to be linear on a logarithmic scale for many events and distances. So to put order there. And here I'm reporting the written text out of an interview which Charles Richter gave a long time ago, and it was actually following the suggestion of Benno Gutenberg. It was saying, okay, if you have a messy cloud of data, let's try with logarithm, because usually it's putting some order. And okay, so I decided how to call this quantity here that can be released. Okay, let's call intensity. No, this can be confused with other intensity, like intensity scales. So since they were, and Richter was a good astronomer as well, well, he said, okay, let's use the same name that astronomers are using for luminosity of stars. So let's call it magnitude. So that's the origin of the idea. And this is a sort of a practical implementation of that. Now let's give a look to a couple of signals here. We have an earthquake A and an earthquake B that may have different distances, different energies. Let's see how to compare these two. Okay, you see now at a glance that they are very different. Look at the content in surface waves, in the frequency, in the other issues. What can we do with this? Okay, first, with very basic seismology, usually I make you to perform an exercise like that in wave physics. I don't know if Lapo touched this part, but with very simple Earth models, you know that from the difference between the arrival time of a P wave and the arrival time of an S wave, they are very different as a feeling. From that difference, you have an estimate of a distance. So you measure here this, and you can convert it. Roughly, it's times 7, but okay, you have a measure in seconds, you multiply by a conversion factor, and you have, at first, a distance. Okay, then let's take the peak. And Richter was very aware that the Wood-Anderson has a transfer function, and it's around 0.8 seconds. It's peaking around 0.8 seconds. So the waves that are collected by Wood-Anderson are transferred by the instrument. By the way, he says, okay, now let's take the peak amplitudes. And what to do? Okay, let's take this time, let's take a conversion in distance, and let's say that these two events have the same distance because they have the same TP minus TS minus TP, TS minus TP, it's the same. Now let's take the maximum amplitude here in millimeters, and let's put on a different ruler. Okay, well, actually, the A0 definition corresponds to put a ruler between them so that when it's touching, it's giving to you a number. So you see the amplitude here is smaller, here it's larger, you connect this, and you measure here the magnitude. That was the idea. Be careful, because the A over A0 originally, also if no one in practice use as anymore, is based in micrometers. So please, if you join the same thing here, you go to 0, 1, still you're getting a magnitude, but if you imagine to go to micrometer, this will touch magnitude 0. So magnitude 0 does not mean zero energy. It means an earthquake which is able to produce at that distance an amplitude of 1 micrometer. So it's not 0. It's equal to the reference value. Okay, this is the history of magnitude at its starting, Richter's magnitude. And since he was aware that the numbers that he was using, so actually the position of this ruler here, was tailored to a Wood-Anderson and to the geological conditions of California, he suggested the idea that this was a local magnitude. That's why nowadays Richter's magnitude, the original one, is reported as ML, where L stands for local. Are we okay?
Yes.
Yes, yes.
Okay, that's, as you can imagine, it's not the end of the story. Because, okay, people was aware, collecting data, that the instrument was important in revealing these amplitudes. For example, here you see a sketch of two signals, well, actually two signals, but the same earthquake, the same recording, but as it would appear on a Wood-Anderson and on a modern broadband, and look at the magnification here. So, well, we have to take care about that. And we have also to take care that the amplitude can be very different in terms of body waves and of surface waves. Okay. But before going to the next definition of magnitudes, now we can have a sort of parallel way to use intensity and magnitude. And that's why I was putting here as an example this parallel way, but please, every year I'm tempted to remove this slide here because this slide here is wrong. Not necessarily a magnitude will correspond to an intensity. Because, as I told you, intensity will depend very much on geological conditions, on vulnerability conditions, on the presence of urban habitats, and so on. But if you want to have a rough idea, okay, that's why this slide is here. And this slide is also giving us a sort of a feeling of descriptors for different intensity degrees. And this is comparing the modified Mercalli that is used in US with the original Richter's magnitude. But again, this slide here is just to give an idea, because in principle, not necessarily there is a correlation between a magnitude and an intensity. Of course, they are correlated, but let's imagine to have a magnitude 6 in the desert, you would get 0 intensity as a paradox. Okay, let's move on. How to define the next scales? Well, let's follow history. And history, as we discovered during the last lecture, knows that during the 60s and the 70s, there was a huge accumulation of data. New instruments, computers, whatever, and so on. Okay. Oh, okay. Is it changing? Yes, it's changing. Let's go to the definition. The next, and maybe the last, definition of magnitude in the classical sense. The classical sense is, okay, now we have different instruments. We have the WWSSN, let's imagine to be the 70s. We know we cannot distinguish better between the different wave fields. Now let's take two different scales. Let's measure the amplitude of body waves, and let's define one. Let's take the amplitude of surface waves. Let's define another one. And let's remember that body waves usually are richer in relatively higher frequencies than the surface waves. So that's why the last instrumental definition of magnitude is made like that. And it's bad in the sense that, for example, you see that the argument of a logarithm is not a pure number. Mathematicians should say, wow, what's that? By the way, in seismology, we are rough people. So you have to take the amplitude that you're measuring on a seismogram, filtered around 20 seconds, so that you can measure better the surface waves, and you take that. So T is equal to 20 for surface waves. If you take that amplitude, you get MS. If you take the amplitude of body waves and you look at the signals around 1 second, let's call that MB. So now here we have a complete set of instrumental. Well, it's not complete, there are other ones, but let's forget about them for today and for this course. This is the general form. You see that there are still some correction factors that should take care about source depth, for example. If you put an earthquake deeper, it will be less effective in generating surface waves, for example. We have to correct for that. We have to correct for distance. That's Richter's original definition. We can correct for conditions at the site. We have to correct for conditions in the source region. That's why also nowadays, the definition of magnitude is not easy. So when you see a bulletin and you look at the magnitude 6.2, please remember that there are physical uncertainties there. So also with this definition, actually, we have many factors that could affect the uncertainty of a magnitude estimation. But that's the definition. And to give to you an example, if you want to take, having that in mind, if you want to take a recording here, you have to imagine that MB is measured with first arrivals, short period, 1 second. MS is measured with surface waves, later, usually stronger, longer period, dispersion, and you take this. So different views coming from from the same signal, but giving different numbers. So you could say, okay, but all the numbers describing one event should be the same. ML, MS, MB, maybe they should give the same number. Well, that's not the case. It's not the case because sometimes we have uncertainty, but maybe they can overlap. But in other cases, maybe there are physical differences. For example, let's imagine to have a source that is not a pure tectonic event. Maybe it's a volcanic event, or maybe it's related to a nuclear explosion. Now you can imagine that an explosion is much more efficient in generating P waves and body waves than surface waves. So that for a nuclear explosion, you should get very large MB values than MS. And that's why sometimes MB is still used to distinguish between explosions or other sources from tectonic events. That's one factor that is causing the difference between MB and MS. But there is another one. And this is what we are going to develop in the next slides. Because actually, if you take some events, especially the large ones, you can see that the numbers are not the same. They could be very different, like in these two examples that occurred in 1999. So if you take the Izmit event or the Chichi Taiwan event, you see, well, MS is much larger than MB. And actually, experimentally, you see that you never get values larger than 6 point something, let's say 6.5, 6.6 in MB. Never. You cannot push up after a given value. So you can say, oh, MB is saturating. And you could say, oh, well, but MS is not. No, it was noticed in the 70s, but also MS was not going to reach values larger than 8 point something, let's say 8.2. But especially in big subduction zones, there were hints that the source was larger so that the magnitude should be larger. But okay, the roof was standing there, 6 point something, 8 point something. And this is the starting of the final part of the history about magnitude. That is how to overcome this effect of saturation. So just a word this line saying, okay, what is wrong here? Well, answer number one, earthquakes are complex. So squeezing everything in one number, maybe it's not proper to do that. So you're trying to use simple numbers to describe a complex phenomenon. Yeah, that's an answer. But maybe with a better definition or with a different definition, maybe we can have a glimpse of larger sources. So I leave to you with these word slides here. Let's go now directly to the point. This is a sort of a written text about what I was telling to you. And well, okay, this is a typical example of saturation. So for example, you see here two different earthquakes that we would label nowadays with 6.1 and 7.7. But for example, they are very different, as you can see. Well, of course, the later part of the signal is very different here and here. But if you take the beginning, the early part of a signal, and if you give a look to the place where the definition of MB is taken, well, they are pretty much the same amplitude. Why P are not getting larger? Question number one. And later the question is, okay, why surface waves are not getting larger than a value after 8.2? Okay, that was saturation. And if you want, that's the summary of the problem. Because the measured magnitude was creating a sort of a roof, while in the mind, there was an idea of a magnitude scale that was not saturated. Where it's coming, that idea? Well, maybe from that picture there. Because after the representation theorem, after the papers by Norm Haskell, well, we know that M0 is not going to stop. Please remember the definition: the area times the amount of slip times the rigidity modulus. Okay, so larger earthquakes should have larger M0. Why magnitude? The measured magnitude is not overcoming these limits. That's the key question for today, and we have the answer. Actually, the answer is explained, I hope, in the next slides. But you should say now why saturation is there, looking at that. Wow, it's terrible. To my plot there. My plot is terrible, but the idea of the source spectra is not, because we have corner frequencies there. So actually, when we consider large events, as I will try to explain to you now, well, M0 is increasing, the floor there is increasing, but at very long periods, because before, the corner frequency was truncating the radiation effect. And we have to keep in mind the two periods at which MBNMS are taken: 1 second, 20 seconds. Okay, please, let's keep that in mind. And what we're going to do in the next and semi-final slides is now to take a walk together with Mr. Kanamori, with Kanamori-san and Anderson. Because after a paper that they published in 1975, and later Kanamori published a paper with the definition of the new magnitude, we're going to take a walk with them, with their ideas. But the ideas are the same that we already have discussed with, for example, the Haskell model. Okay, that's the key picture for today. It's here. Now, this is nothing else than a replot of the source spectrum, but now with a different view and a different, how to say, labeling there. Now you see the logarithm of frequency, the log of M0. Be careful about the units, I'm sorry for that. In many cases in seismology, we're so unpolite, but we're still using a CGS system. So if you give a look to M0 expressed in dyna times centimeters, you should go back to the good old, unpolite word of CGS units. So sometimes it happens. One question to you. Are you there?
Yes, yes.
Can you convert dyna centimeter in Newton times meter? This question is about a sort of a bachelor of physics, but can you imagine how to do it? Well, okay, you have an additional homework. It's going to take 10 seconds. But if you convert a centimeter in meters, that's easy. And the dyna in newtons, that's okay. You would get that a dyna centimeter is 10 to the minus 7 power of Newton times meters. So please look at this. If you want to express in Newton times meter, you have to get 7 out of these numbers here. But physics are not going to change, by the way. So that's the logarithm of f. So 0 does not mean 0 frequency, but 1. And now if you plot the source spectra for increasing earthquake size, now you see immediately that, for example, at 1 second, you reach this point, you can get larger earthquakes, but that amount will not change. So saturation is related to the fact that at 1 second, the amount of energy is not increasing with the earthquake. We are reaching the roof. And then you could say, but wait a second, that's 1 second. Let's go to longer periods. Let's go to 20 seconds MS. Oh, good news here. But sooner or later, you will touch the roof also there. So actually, what's going on there is that all the large events here, they were getting lower and lower magnitudes because we were saturating due to the fact that we were touching the maximum level of the source spectrum. So now you should say, okay, good. Can we go to a domain where there is no saturation? And you could say, yes. Let's go here. Because if we go to 0 frequency, what does it mean? Infinite period. Then that will never touch the floor because M0 will increase. Do you agree with me? Are you there?
Yes.
Yeah, we are here.
So, please tell me, do you agree with me that if we measure the radiation at infinite period, we are done? Because here, the roof will never be touched, because here we have M0, that in principle can increase up to what the nature decides. Okay, I hope you do agree with me. But also if you agree, and if you agree with me, but not with me, I'm not important, but with Kanamori, that was using this idea to define MW, you could say, okay, game is over, we're done. MW can be defined using the estimation of M0. But it's never saturating. But you should agree with me that in practice, to measure M0 is not an easy task. And that's the final practical issue with which I will leave you with your nice reading that is your homework. But before going there, let's make the final steps about this definition. And the final steps now are going to use a tiny piece of theory that we already developed. So the next 4 slides are the worst one for today because they are using or recapping the theory that we have been using in some new parts. Question to you. Do you have questions?
Not yet.
Okay, good answer. So good question. Not yet, because maybe you will have in 3 or 4 slides. Now, what we're going to do is I try to prepare here a sort of a summary of a Kanamori and Anderson paper of 1975. I'm still also using, as in your textbook, by the way, the same pictures that they used. Now, let's try to put some order here. What Kanamori and Anderson did at the time was to consider the largest earthquakes that they had, where in the 70s, instrumental seismology was, okay, running, computers, well, slowly compared to nowadays, but they were running, and they were trying to think about them. And they used some definitions that are still used today. to put order. And let me try to wipe something here, to wipe the blackboard, if needed. Okay, so we had been saying, good, let's take a fold. Let's take the area. The area is L times W. I'm using S here and not A because they used S in their paper. Okay, now let's take the average slip that is entering into the M0, and let's compare with the length. So it's a slip over the length. We can call that a sort of a strain. Strain related to what? To the earthquake. Let's call it strain drop. Now, if we have a strain, we can compute stress. And stress is strain times an elastic constant. And since they were dealing with tectonic earthquakes, they defined the stress drop as this quantity here. Mu is the rigidity modulus. C is a constant that depends on the size, on the shape of the fault. Okay. Then they said, okay, let's imagine that all the earthquakes, they obey to some similarity conditions. They call them scaling laws. For example, W over L, their ratio, is a constant. So earthquakes' size is increasing with a sort of a ratio. These are very simple, not always valid laws, but they use just to have an order in mind. And then they said, okay, and also the amount of slip over the length of a fault, they are constant. With these two conditions, we can rewrite M0 in different ways. For example, like that, that's the basic definition. We can rewrite it as that or as that. So they were looking for power laws describing, connecting M0 with something that could be measured, like the length of the fault or like the area of the fault. Okay. And then they said, what about the kinematics? Well, they call the dynamic similarity, but actually it's a kinematic one. Okay, the two kinematic times, tau and L over VR, that is TR, the ratio is another constant. So just to have very simple ideas about earthquakes. And then they began to plot things. And just to relax you, let me just tell you that this path is explained also on your textbook, from which I was grabbing this slide here. And this slide here is giving us something more in detail. For example, the rupture time can be approximated like that, you know that. The rise time can be written in a different way, something like that. That's the stress drop. And just to have an idea, if you have a shear velocity of 4 kilometers per second and you have an average rupture velocity, you have these estimates of rupture time and rise time. Okay. Picture number one. They were plotting the logarithm of M0 and log of A, because the theory was saying, oh, those two logarithms should follow a linear slope. Good. And you see, they had been using the data at the time for the large earthquakes. And if the stress drop is constant here, okay, that's giving to you the intercept of this slope. And they are following a line. Okay, good to know. And so they said, okay, now let's give a look now to magnitude using this scaling relationship. Now, what about magnitude? All the definitions, the Richter, but especially the MS, because MS was the most important magnitude to be used at the time, actually are based on the logarithm of an amplitude compared to 20. Do you agree with me with the previous definition? Okay, I can go back with the slides, but essentially magnitude is this, with t 20 seconds, okay?
Yes.
Now, 20 seconds is a time, is a period. Now, what about TR and tau? Is it longer? Is it longer or shorter? Well, for the large earthquakes that we have in mind, this should be shorter than this, and this should be larger than this for large earthquakes. Okay? And now, what about that logarithm of A compared to that 20 seconds? Okay, here comes the rest of the story. Because they used the expression of log a day that we developed 2 lectures ago, the source spectrum. Because you see on that picture there is the logarithm of A. And the corner frequencies are related to 1 over TR and 1 over tau, right? Now let's give a view to the magnitude definition using that and this idea. And that's the messy slide. I spent 1 hour to write it. Now, the first panel is coming exactly from our old lecture. The source spectrum average with geometrical spreading and radiation pattern is M0 times a function that is the product of 2 sinc functions. You do remember that, I hope.
Yes, yes.
And here there was omega, and here there was tau, omega, and this is TR. And if you do remember, we played the dirty trick of saying, okay, the sinc function is 1 until x, or using sine of x over x, and 1 over x after x. So now, using that definition, and we already used it, we can separate the different behaviors of these sinc functions using the fact that the rise time or the rupture time are smaller or larger than that value t. Now t, capital T here, is omega. Omega is 2 pi over t, so that is t. So I've just been rewriting that expression in a different way. But now if you give a look to M0, 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 and these times here, you can separate these 4 different domains, and you would have different scaling laws, for example, with length. So the first part of this picture is nothing else than a rewriting of the last one. But now the final step is the following. Since magnitude is the logarithm of the amplitude, so this one, and used as a reference 20 seconds, now we can have in mind 20, and to express those 4 situations that we have here into 4 different quadrants, where we have logarithm of A, we have time, like there, and to see what happens. Wait a second, because the 4 quadrants that we are looking at are very different. For example, here, tau is less than t over pi. Let's take 20, let's take 21. Divided pi, that is 3, I'm sorry, that's 7. Okay, tau usually is less than 7 seconds. And rupture time usually is not less than 7 seconds. This domain here, tau is larger, and this is smaller. That's not for the earthquakes. But what about this? Oh, yes, rise time is less than, rupture time is larger than. And these different domains correspond to different behaviors, scaling with length, M0, and area. So something that could be measured. The summary of all this mess is in this picture here. Now, they took all the large events that they studied, they put a plot. Here we have, in our jargon, this is rupture time and this is rise time. And here you see the line of 20 over pi. As they were waiting, as we are waiting, most of important earthquakes fall in this quadrant here, where rupture time is larger than 7 and rise time is less than 7. So they had a confirmation. And here was still a mess. And they used this. It's a consequence, because you see, this quadrant here is this. And so the theory is telling us, okay, for earthquakes, M should go with 2 times the logarithm of the length of the fault, 2 over 3 the logarithm of M0. Oh, that's it. That's it. And so, after this work, Kanamori said, okay, my friends, now, since MS is saturating, let's use this relationship here to define a new magnitude. We take the logarithm of a moment of an earthquake, and we multiply by the slope suggested by the theory, that is 1 over 1/5, so 2 over 3, and let's use it to define magnitude. So the final step is the following, and it's a sort of a summary of many things here. Because starting from many ideas, and I will going to tell you, Kanamori said, okay, it's not important to use A and T measured in practice. Let's try to measure M0. Let's take the logarithm. Let's multiply it by 2 over 3, and we got a new M. So it's a reverse, not from magnitude to moment, but from moment to magnitude. And they say, okay, how to fix, now we have a slope, how to fix the intercept? Well, the intercept has been decided in order that at magnitude 8, MS is giving the same amount of MW. And the final formula is this. Pay attention, because 6.07 is valid when you use Newton times meters. If you use dynacentimeters, that's the number here. And why they used this? Well, because in the past, in the most important textbooks, like the Gutenberg and Richter 1956, there was the idea that magnitude was a measure of the energy of an earthquake. And actually, they used this kind of formula here. And you see, from an empirical view, they found this 1.5. And Kanamori and Anderson found that 1.5. Theory is suggesting 1.5, so let's take it and let's define a magnitude. Legend says that W stands for work, and you can remember it because it's moment. Moment is, okay, it's a Newton times meters, but actually Kanamori said that he preferred to use W because it was one of the first letters that was available. So MW in principle is a new, totally new magnitude based on theory, so spectrum. M0 is never going to saturate. Let's take M0, let's take the logarithm, let's multiply by 2 over 3, and let's, okay, use this intercept to get the number. here I'm simply adding one idea, that was again in the back at those times, it is related to one of the attempts that Gutenberg Richter did to see why the energy of an earthquake was connected with the, for example, with A over T. Because, for example, if you take an harmonic signal like this one here, and if you compute velocity, you're going to get an A over T. Of course, you have an omega there. And so since energy is the, for example, kinetic energy is going like the square of the velocity, okay, you have this. And if you take the logarithm, okay, you have something that is going with the logarithm of A over T. That was the idea that was in the background for this. And so the summary is something like that. Different empirical, if you want, instrumental magnitudes that are saturating. At 8, MS and MW are there, and in principle, MW is free to run wherever. And now if you get a look to the numbers and to the estimate of the moments, now you see that many saturated events, now they are free to run up to 9.5. And that is the largest earthquake in terms of MW that is supposed that occurred in human history with all the uncertainties. Now, in the last 10 minutes, now we are going to run because otherwise I will be late, but let's take just a view about how the logarithm is squeezing. Remember, logarithms are squeezing. And here, what is funny is that Stein was putting together many important earthquakes in the past and their differences. And okay, MW, remember, is a logarithmic measure. And so you see how you're jumping from 9 to 6.7 with orders of magnitude there. And actually, remember also that due to this logarithmic nature of magnitude, that if you give a look to the global seismic moment release from 1906, the first instrumental earthquake, to just in the after of the Sumatra event, if you give a look to this pie chart, you see that the giant part here is related to mega earthquakes here. And if you go to sum, if you're summing all the events with tinier magnitudes, you see the pie chart, the pie section is much smaller. I tried also to update this one with this. I hope it's going to work, okay, after the Japan. And with a sort of a different, sorry, it's Italian, Japan, it should be Japan. Okay, sorry for the Italian there. But you see how the slices of energy are impressive when you write out the logarithmic behavior. Now, let me conclude before a final thought with two messages, additional messages. So, main message today was MW, okay? That's the message for today. So you have a set of magnitudes now. M, Richter, you can call it ML, MB, MS. There are other ones, it's not important. And MW based on the logarithm of a moment. So apparently we're done. There are 2 or 3 general concepts that I want to leave to you. The first one is, okay, just to have a glance of the dimensions here, I was grabbing this cartoon from a very famous paper that is Wells and Coppersmith. It's coming also from your textbook, that is giving us an idea of slip and dimensions of the fault. For example, let's take a magnitude 8. And if you go here, these are empirical, you go here and you see what is the average length. Let's see, 200 kilometers for a magnitude 8. If you go here with 200 kilometers and you see what is the average slip on the fault, okay, it's about meters. Now let's go to magnitude 7. Here you have, okay, let's say 80 kilometers. If you go to 80 kilometers here, it's meter. If you go to magnitude 6, okay, let's say 10 kilometers, and the slip here is, okay, much less than 1 meter. If you go to magnitude 9 here, you go to 1,000 kilometers, and 1,000 kilometers is going to 20 meters. So please remember, so I put here some very rough numbers here, about the orders of magnitude. And there is one other factor that we should consider sometimes. Okay, let me skip this part. Maybe we're going to discuss it later. But what I want to, later or the next lecture, there is another issue here, is about the number of earthquakes. Now, the number of earthquakes depends on magnitude as well. In this cartoon here, the plot is showing us as a sort of a negative exponential behavior. But what is evident, what is maybe not so evident in this plot here, but is very iconic because it's comparing the energy in terms of the moment magnitude here, the number of events, and compared also with the energy of other natural or human events here. But what Gutenberg and Richter immediately recognized was that the number of events was going with magnitude, but with a very impressive fashion. And it's called the Gutenberg-Richter law. The last two concepts in this lecture actually are representing a bridge to the lectures that we're going to spend on the next week. Because this law here, and I will just say a few words about it, it is very important, has a deep signature on seismic hazard. But what they did, what was their idea, was to collect the available catalog, seismic catalog, at a global scale, and to measure the number of earthquakes as a function of magnitude using a logarithm. And they found a beautiful slope with a slope, a beautiful line, sorry, with a slope of b pretty much equal to 1, so -1. You can open a course about the Gutenberg-Richter's law, but please let me tell you, they use this law at a global scale for a given running time. For example, here you see the plot coming from the textbook between 68 and 1997. You see here, cumulative means all the earthquakes with magnitude larger or divided by bins, but the idea here is to have lines here, okay? For a different time here. There are open issues here because this law here can be used in hazard to have an estimate of occurrence time of earthquakes with a given magnitude. It's important in the probabilistic approach. It's used and may be abused. But what is funny about this very simple law that is connecting the number and magnitude, at that time they were using MS, now it's of course MW, is that if you rewrite it as a power law, so if you take 10 to this power here, and you use the relation that we found here, actually you can find a beautiful power law between m and moment. And this power law has an exponent that is not an integer. And usually this is leading to fractals. So this is just a hint. Some of you is going to study seismicity in terms of statistics, because you can find the power law there. Gutenberg-Richter is a never-ending story because, especially for hazard, there is a debate, it's still active. And I don't know, you can ask Karim when in his course about what is the end of a Gutenberg-Richter. Is it ending like that and then stopping? Or is it behaving like that or like that? Because in this case, you may have different hazard predictions of course. What is the largest magnitude that we can have in one area? Okay. That's an issue. By the way, in its simplest form, GR law, because in many cases it's used as GR law, is given by two parameters: the intercept that is connected to the seismicity of the area, okay, and the slope that is deciding what is the largest magnitude in that area. So this is one of the messages that maybe we are going to open in one of the next lectures when we will speak very quickly about the seismic hazard. But the final message that is a bridge to next Monday's lecture, okay, that's the summary, is before, oh, where I put it? Oh, I was hiding it. Okay, wait a second, just as a prequel. Okay, the prequel is here. Because on Monday, we will speak about Q, and we see a trace, a tiny signature here, because we understand that the effects of an earthquake will depend upon the Q of the world or the region where the earthquake is occurring. So we will try to study anelasticity from a theoretical point of view to understand what is the Q of the Earth, but that will leave a signature also for seismic hazard studies, as you can see from these two pictures. So this is what we are going to develop on Monday, Q, and a plot. I want to show it to you. Oops, no, I don't want to do this. Oh my God, this is, okay. Okay. Look here at this picture. It's supposed to be one of the final pictures for Monday. But what you see here is a peak value of the motion and distance. Actually, this is a plot very similar to what Charles Richter did, logarithm of the peaks and distance. Well, actually, in seismic hazard, this is called attenuation law or attenuation relationship. It's used for hazard estimation. And if you give a look to this curve between eastern and western US for the same magnitude, you see that the decay and the amplitudes are totally different. That's Q. So that's one prequel. The other prequel, so it's about Q, actually will be about hazard, where the GR law sometimes enter in the computation. But the summary for today was magnitude, but now we should be able to relate it with energy of an event. And let me, otherwise I feel guilty here. This slide here that is coming from, okay, let me spend just a few words about this slide that I was skipping here. Because as we computed in that part, as we have used for the scaling laws, we know that moment is actually related to the release of energy that is accumulated there under tectonic forces, friction, release. So it's energy emission. And the energy emission, the total energy emission, actually is related to, if you want, to the stress drop times the slip times the area. Please remember that part of the energy is spent in friction. So in this slide here, please remember that part of the energy is not going to be radiated as seismic waves, but is going to stay there in the friction law. Now, the percentage of radiated energy over the frictional one is called seismic efficiency and depends over the stress drop. And following this very simple computation made by Seiwa's session, if you want to measure, to have a quantity about the energy released by an earthquake, this is important, related to the stress drop and the moment there, okay, that's the amount. And you see that the radiated energy in terms of seismic waves, on average, is a very tiny amount. And here there is another important issue, because this is the summary for today. Look, this is in centimeters. Because actually, if you consider one step in magnitude, one increase here, please, for example, from 5 to 6, and you convert it in energy, please remember that we have a factor of 32, because we have 10 to 1.5. So this means that one step, remember that magnitude is a continuous scale, one step in magnitude means that we have a factor of 32 here, and this means 1,000 factor in energy released. And that is why I'm going to close with some minutes of delay here, showing to you the Moodle website, just to describe to you what is your very nice homework that is represented by this. Actually, it's this one. This is a similar paper published for the Tohoku event. But look at this. And this is the key picture here. Because they had been using, the short story is that they had been using the longest available periods of seismic radiation to really estimate moment magnitude. You know why? Because on a routine basis, this definition of MW is beautiful, but in practice is